So continuing with trying to frame this concept of pack learning that we just defined, let us try to use the concept of Boolean functions, which we've been studying for some time now, and try to learn them. So that gives us something quite concrete. What are we learning? We are trying to learn a Boolean function. So given that we have this pack framework which talks about how well you can learn through epsilon, for example, what confidence you have to this parameter delta, we'll now try to apply those concepts and make them concrete. And so given what we already know about Boolean functions, we'll try to just do a 5-minute recap of what we have seen in the past, including their representations through their Fourier spectra. So given a function f, informally our goal is, we say, to figure out, which is to learn, given some evaluations of f, which means you can substitute inputs or give inputs to f, look at the outputs. Clearly, if I give f all of its inputs, that would imply I have learned f fully. That's too expensive, as we will see, because there are two. If you look at the bottom of the slide, there are 2 to the n subsets, which 2 to the n elements that you'll have to try, and that's expensive, as we know. We would like to be in keeping with the spirit of the course and the rationale we developed during the first portion of the course. We would like to be, in terms of complexity, polynomial in the main parameters that we care about, n being one of them. So the way we defined the Boolean function and the way we wrote its representation through its Fourier spectrum is the function f. You had the terms f hat, which are the Fourier coefficients, and these are applied to different subsets of the actual set. So x sup s, we already remember the terminology. I won't repeat it now. And we note, of course, that this set under the sum, the subsets can be as many as the power set. So you can have up to 2 to the n subsets of this base set S that we care about. So this is a reminder of exactly what we studied in a whole lecture, in particular the second lecture of this portion of our course. And now we will try to use this form as a basis for defining efficiency. So what we're trying to do is to look at a Boolean function f, and instead of saying something simplistic, such as I can look at all its inputs and I know what f is, we will instead look at something hidden, its Fourier coefficients. So just a one-slide summary, a Boolean function f in our form takes n vectors or n tuples ordered with elements in them -1 and +1 and maps them into a single value of either -1 or +1. And we already gave justification for this. So we also know that its Fourier expansion can be written like this. And just to remind you again, there's a whole lecture, so I won't go into the details. The term x sup s is the product of the elements of that particular subset that we care about, all its member elements, xi. So that's how we define it. So now we will try one by one and map our definitions from this very general pack model that we introduced a few minutes ago into being useful in the context of Boolean functions that we are trying to learn. And we will come up with a form of a theorem in this particular segment stated informally about what it means to be efficient in pack learning. And people use this term quite often. If you say that something can be learned well by a pack algorithm, people say it's pack learnable, and the process of doing that is pack learnability. One element that's particularly interesting and also useful to our data science portion of this is this concept that we dwelt on when we were looking at the Fourier expansion of Boolean functions, the concept of sparsity. So sparsity means there are only a few important pieces of this function that determine its behavior. And this, as we recall, and we will look at this again, can be determined completely by its Fourier coefficients. And if only a few coefficients are important, one hopes, then you can pretty much learn the function quite well. And of course, this needs to be quantified just by looking at those coefficients. So sparsity means, in this sense, the ability for us to be able to look at the function's overall behavior based on a few of its coefficients. So to do that well, we have two concepts that we will talk about. The first is the concept of epsilon concentration. And informally, it says that the squared sum of the coefficients of a given function is small, and it captures informally for us the idea that the collection f, which is a subset of the terms of the Fourier expansion, contains all the interesting subsets of S that we wish to focus on in order to be able to capture f. So formally, let f be a collection of subsets of S, and we say that the Fourier spectrum of this function f, which we have already defined, is epsilon concentrated on this set f, provided the sum of the square of the weights, that's for, you square because you want to normalize and get rid of things like signs, the sum of the square of the weights of elements that are not in f is less than equal to epsilon, which means most of the weight is in elements that are in f. Elements that are not in f, if you add some property, in this case the square, of the Fourier coefficients, then that's less than equal to f. Just as a reminder, on the same slide, we saw this a minute ago, the way you would write out f of x is as a sum of f hat s over a range of subsets of this, and it was a weighted sum of those Fourier coefficients. F, the set that we are talking about in defining epsilon concentration, happens to be a particular subset of the power set of all the elements 1 through n. In defining pack learning, we had also defined an error function in order to quantify, if you recall, how close the concept we are learning, C, is close to the hypothesis H that our algorithm, in that instant, we used the letter A to define it or denote it, how close H is to C. We would like H to be as close to C as possible. For historical reasons, the terminology used in learning Boolean functions is slightly different because there is a little more specificity to a Boolean function. It's not some arbitrary concept, but it's rather a particular concept. So what people say when they refer to error in the sense of pack learning is distance when we apply pack learning to Boolean functions. So if you're given a function f, which you're trying to learn, that's our concept, and you have a hypothesis, which is another Boolean function, obviously, which is h. It's very similar as to what we had defined before. The distance function between h, the hypothesis, and f, the function we wish to learn, is the probability of h not matching f for particular inputs when you draw, in this instance, inputs to the Boolean function x. That's what this symbol is saying, this particular notational form is saying, I should say. when you draw them as part of a distribution, we had used the letter D when we discussed pack learning. And in this case, we are talking about a uniform distribution. So D is a uniform distribution. So it's exactly the same definition as error in the context of pack learning, with the concept being the function f we wish to learn, and the distribution being a uniform distribution. Otherwise, it's the same framework, we should say. So now we are ready to actually postulate a theorem in a simple form, which I'll state informally now, and then in the next segment, which is the next lecture actually, we will be looking at this formally, including a sketch of a mathematical proof that establishes it in its entire form. So we have a learning algorithm A, and now I'm reading out the theorem, and it's given random examples as before, accessed through, let's say, some oracle. So somebody tosses out these examples to you, and you're allowed to now plug them into F and get its output value. And suppose that somehow A can consult somebody, and this somehow part of it is something we will be formalizing later. But for now, let's say that A identifies the subsets F on which its Fourier coefficients are not epsilon, but in our case, epsilon by 2 concentrated, half epsilon concentrated. Then what we can say is, using polynomial time in the size of this subset F, where the Fourier coefficients are concentrated, n, the size of the formula, and 1 over epsilon, our algorithm can, with high probability, which is the confidence delta we used to have, output a hypothesis H that is epsilon close, bound to be within an epsilon of F. So we will see in a few minutes a detailed example of this, but for now, the main ideas that we are talking about here are two in terms of interpreting pack learning. First, we are talking about the concept of using a few terms of the Fourier spectrum of the Boolean function f we are trying to learn. And second, we have this concept of error, which is interpreted to be distance, and that's epsilon. And through that, we have a framework for talking about how well we are learning, which is this polynomial in the three terms we have so far, with high probability, which implicitly gives us delta. So what does this statement mean? What this really means intuitively is that if the target function f is sparse, and therefore you have just a few coefficients, polynomially many, let's say, in n, then its spectrum is concentrated on those coefficients, we can efficiently learn f in polynomial time. The reason is that the polynomial, the way we defined it, is in the size of f, the set of coefficients that matter. If that set is too large, if it's exponential, say, being polynomial in that is not very interesting, because we want finally the entire learning scheme to be polynomial in n, the number of bits in the input. So continuing, the learning, if restricted to f, would imply that we do not look at other coefficients, but rather just look at the coefficients in f. And moreover, to close this argument out, we are able to do this with high probability, and hence the parameter delta that we had, which was the confidence, is also built into this statement now. So to pull it all together and say it informally as one sentence, knowledge that f is sparse gives us an efficient algorithm to learn f. So here is something that's very interesting in a connection to what we've been mentioning a few times now, to data science. So one of the main goals of this phrase, and it means different things to different people, is that you have lots of data usually, and you're trying to find structure in it. But you want to find structure efficiently. you don't want to be exponential in the size of the data set. It also is the case, and it turns out that's helpful, that quite often when people talk about big data, the amount of data that you have may be large, but the amount of meaningful information in it is not. As a result, sparsity, in the sense that we've been quantifying through the Fourier spectrum and through the concept of being concentrated on a few variables, is very important, because if indeed a given function, in our case a Boolean function, is sparse, it means that we are able to learn it well and learn it extremely efficiently. So now we have pulled together two different completely independent threads we had developed in these previous lectures. The first being the concept of sparsity, represented precisely through the number of dominant terms in the Fourier expansion. And second, the concept of pack learning, which pulls this together and uses it in order to be able to learn Boolean functions and learn them efficiently. So now we are beginning to have a complete mathematical framework for addressing and exploiting sparsity on the one hand, while being able to talk about efficiency of machine learning on the other. So to informally prove this, what do we have? We know that the function is epsilon by 2 concentrated on some collection f. We also know, therefore, that we need to estimate the Fourier coefficients on these sets only, the sets that are representing the concentration. And moreover, to look at the other side of that statement, because the other subsets are guaranteed to have small coefficients, which is bound by epsilon, that's the definition, which gives us hope for finding an efficient algorithm. So going back to the pack model, because we're trying to wrap that model around this concept of learning Boolean functions, we had also this example generating oracle, which, given the concept C, which for us is the Boolean function, and the distribution D, which for us now is the uniform distribution, it generates examples. So we are implicitly still using such an oracle, and if we can generate the Fourier coefficients that matter, which we left as a conditional statement, saying we may somehow be able to find them, then two questions arise. First, how do you build this approximation? And then second, how good an approximation is it? So without going into the formalism, because that's the topic for the next lecture, very briefly, what we will be doing is, we know that f hat s is defined, going from our old lectures, to be in this form. So given an n input function, we have 2 to the n possible inputs, and to recap, using all of them is expensive, which is the whole point of what we're trying to do now, exploit sparsity. So a reasonable approximation, instead of finding all the coefficients, 2 to the n coefficients, and then looking for the dominant ones, is intuitively to average the values of this on the samples that we do have, and use that as a basis for deciding what to do. And we'll see this in detail, but that's the intuition. And then, if this averaging is any good, how close an approximation to f of x can we obtain? So what we will now do is to actually take a concrete function and step by step walk through these abstract concepts we just described, and then try to derive, in the sense of an example, the particular attributes we need and care about. So let us say that we had and to simplify in the example, we are giving values to ourselves. So let's say that f is a function on 3 inputs, and let us say that, as I said, if somebody were to magically give us f hat, let's say the subset 1, subset 2, those were the values, and all the other subsets in this particular case, let's say, had 0 coefficients. We also have random access in the sense of being able to generate examples randomly through this oracle. So our oracle in our case gave us these 3 examples with the particular evaluations you see for f to be minus 1.4, minus 1.4, and minus 0.2, let's say. So this is in this example. So we have 3 inputs that our oracle gave us, in this case out of a possible 8. And we also know that the Fourier coefficients of this are 0 everywhere except for sets 1 and 2. Yes.